Welcome everybody. It was talk in terms of week. First of the 8 talks that we're going to have. We're happy Madhu is starting it off. Madhu is the faculty at Harvard University, he's a frequent visitor here. He's speaking on, I'm not going to describe, give him more. He's going to speak on sparsification graph courses.
Great. Okay, thanks, Pranav. So it's always nice to be back here, and it's nice to see the number of co-authors in this room is increasing over time. So Raghuvansh is another frequent collaborator, and also kind of making it hard for me to find topics to talk about. Everything is work done in this room. So anyway, I did manage to find one, and that was this recent couple of papers that I've written with Sanjeev Khanna, who's at Penn, and Aaron Louis Petterman, who's at Harvard. Louis is a graduate student there in the second year, and
Louis is not the institution.
Louis is not the institution. This is the only person that I know that has parentheses in his name. I mean, every paper he writes, he puts these parentheses in there. So, and at least in India, we understand that a name can be any sequence of ASCII characters, right? So, like, it doesn't have interpretations of last name, first name, and so on. Okay, great. So, this theme of sparsification is in the space of compression, something which is much more familiar to many of us. Compression usually considers the task of taking some large amount of information, squeezing it so that you can later on expand it back to the entire text completely. So that would be perfect compression. Lossy compression can be expressed in many ways. One way I'm thinking of is you're given some string X, you can compress it, but afterwards you can't decompress it back to the original string exactly, but to something which is close in some measure of distance. And if you took Hamming distance as a measure, then what you get outside has the feature that you can ask a bunch of queries about this string X, which you don't have anymore. You only have the noisy compression of X.
Noisy, lossy is the same?
Lossy is the same, maybe, yeah. And, sorry, it should have been lossy compression. Yeah. But at the end, you can ask question, what is this coordinate of X? And you will get it right for most of the coordinates. So most of the queries are answered correctly, but only the number of different queries that you can think of is also only polynomially many. In contrast, of course, if you want to ask about any function of X from its compressed version, you can compute that function completely because you're getting all of X back, and so all functions are recovered. Sparsification sits somewhere in between these two areas, which says that somehow we will have a fixed class of queries in mind. These are the queries that we will be looking at, and often we will be looking at exponentially many queries in the length of the string X. And still we would want to compress it so that we can answer all of these queries correctly, but approximately. So these will be real valued queries, no longer just what is the value of this bit. And each one of these queries, suppose it's a non-negative integer, we want it right to within 1 plus or minus epsilon factor. That's the typical nature of the question of sparsification. So what kinds of tasks, what kind of information can you actually sparsify in this sense? It's not something that we study regularly, definitely not something that I study, but yeah.
So for sparsification, the set C is known upfront.
Yes, so the set C is known, but for every query, the set C is a collection of queries, and then for every one of those queries, you want to infer that.
Lossy compression, the queries can.
Well, you could just say it's the collection of all functions. Sorry, lossy compression is also known set of functions. You will typically have something saying, I want this video image to look roughly like a video image, which means certain collection of signals should be compressed properly, etc. So you usually have a fixed set of queries, and then you want to answer them. Only in the true compression, you could say, every function can be computed. Even there, you could say, I know the class of functions, it's all functions.
The answer will depend upon C?
Yes, answer will always depend upon C. And in some senses, yeah, it's probably inherent as well. All right, so let's start with a good example. This is the classical example. Benczur and Karger, primarily Karger, started this line of work where they said that you can compress a graph to roughly linear in n number of bits, nearly linear, like I'm ignoring polylogarithmic factors, but a graph on n vertices could potentially take n squared bits to describe. The adjacency matrix is all theta of n squared bits long. But you can compress it to nearly linear in n number of bits while answering a certain class of queries very nicely. What is the class of queries? I give any partition of the graph, the vertex set into 2, and you count how many edges are going from left to right. Okay. And this quantity will be preserved within a 1 plus minus epsilon factor. Yeah.
The graph is undirected.
In this example, the graph is undirected, yes.
Unweighted.
We will take unweighted graphs, but you can extend all of these things to positively weighted situations. The epsilon will take care of all those cases. But for simplicity, let's just stick with undirected and unweighted graphs.
Wouldn't Gomorigo tree give the exact answer?
To get an exact answer will take you about n squared bits of information. Right?
But if you construct a Gomorigo tree, that's like in-loading with stuff.
Well, then it probably does not give you the exact answer. Because what I do know is that if you want to compute the answers exactly saying how many vertices are crossing every cut, then pretty much you recover the entire graph. That's n squared bits of information.
Gomorigo only min cuts. So the Rohan sounds.
Oh, I see. Okay, great. Okay, thank you. So, one of the key ingredients, and we'll return to this later, the thing is the way Karger proved this, and Benczur Karger proved these bounds by giving a cut counting bound, which says that in any graph whose minimum cut value is C, just has some length value. If you look at how many cuts have value, like at most alpha times that thing, think of alpha as a small positive integer, so on. Says that the number of such cuts is, actually polynomial. For all choices of alpha, this bound holds n to the 2 alpha. And in particular, if you're looking at cuts of size, 10 times the minimum cut size in the graph, the number of such cuts is very small. It's a very, very nice, beautiful structural result. As soon as you have this, you can pretty much say that if I take a random sample of edges of the right size, then small cuts, you have fewer, the probability that an edge will cross a cut, and you're going to sample it is going to decrease because it's a small cut. There are only a few edges that you need to sample from. But on the other hand, the number of such cuts is also small, so you don't have to do a union bound over a large number of events. And this combination works perfectly. It says now from now on, a random sample of the edges of the graph will actually.
That's alpha times the size of the min cut.
Yes, alpha times the size of the minimum cut of the graph. Okay. So big cuts where you have n squared edges crossing the cut, you don't care. Random sample obviously is going to give you the right answer. But if there's a set cut of size, the minimum cut is of size 10, you're sampling cuts of size 100. You want to look at a cut of size about 100 and give an answer in the range 90 or 110, then your sampling bounds better be very tight, and that's what that's why this kind of lemma is useful. Okay. Benczur and Karger use this lemma and along with a bunch of additional stuff, and we'll talk more about it later, to say that a non-uniform sampling of the graph, which means I'll sample some edges carefully and then give them different weights, will also be allow me to tell you how many edges are, give me theta of n, roughly the original promise bound, that many edges can actually capture this information exactly. Okay. I'll come back to these lemmas in more detail later, but just to give a flavor of, yes, there is a non-trivial property that can actually be sampled that can be sparsified very nicely. And the term sparsification has, I'm using it in two different meanings in this talk. In the previous slide, the way I meant sparsification was just somehow reduce the amount of information. It was used as a pseudonym of compression. In this example, you're really saying, I have a graph, I want to take a subset of the edges. So sparsify the graph by taking a subset of edges, maybe add some additional weight information and use it. In all our positive results, this is the notion of sparsification we'll be talking about. We won't talk about negative results in the talk, but when the negative results are alluded to, we'll usually say take any way of representing information, these lower bounds will hold. All right. So what else could be sparsified? So like we said, we want to understand what structures can be sparsified, and structures should always be viewed as some data, like the adjacency matrix of a graph or anything else, but also the set of queries. So for instance, people have looked at notions like graph Laplacians. So this is some real extension of the notion of a cut. You don't just say assign zeros and ones to vertices, but also real numbers in between zeros and ones, and ask questions like what's the expected difference between the length of an edge, the left-hand point of an edge and the right-hand point of an edge, etc. These can be sparsified, and they also get nearly linear size. People have worked on hypergraph cut sparsifiers, saying, oh, look, I have a hypergraph in which the edges are not just between pairs of vertices, but are involving triples or quadruples or etc. vertices. And there have even been studies which say, oh, you can sparsify SAT formulae. So I give you a SAT formula, n variables, m clauses, and each clause is a disjunction of variables or literals. And now I want to say, well, I don't want to see m different clauses. I want just order of n different clauses, or roughly order of n different clauses, which roughly represents the same information as the original formula. And what do we mean by the same information? For every assignment, I want to say roughly how many clauses will be satisfied. Okay. So all of these have been considered in the literature. All of these actually do have nearly linear size sparsifiers already in the literature. And then there are these other questions that you could ask. Well, if you can satisfy SAT formula, can you start sparsifying any constraint satisfaction problem? A constraint satisfaction problem is again given by a bunch of variables, and then I give you some predicate that you're allowed to apply on subsets of variables or subtuples of variables, and I construct an instance by applying the same constraint many times. If I apply the constraint P many times, then I get what's called an instance of a CSP of P. Now can you sparsify this to get back a small number of constraints which capture the original instance? Okay. And the CSP sparsifier question was asked by Kogan and Krauthgamer. They said, well, what can you do? One question that they left explicitly open was, oh, what if the constraints are always XORs of variables? So the variables are all Boolean variables, zeros and ones, and every constraint picks some subset of variables and says, oh, but the constraint is satisfied if an even number of these variables is 1, for instance. Okay. So this kind of a thing they didn't know how to sparsify, and that's the kind of things that we'll be getting to today. So what are we going to do this talk? We're going to talk about some object that was never studied before, which is called code sparsification. Put Sanjeev Khanna and me in the same room, probably this is the question that would come. You have codes and you have sparsifiers. And what we were able to do is actually show that in this case, you can sparsify all linear codes. So what's a linear code? The data here is the generator matrix of some linear code. Okay. And the query here is going to be a message. Encoding of a message by this code is going to be just multiplying it by this generator matrix. Okay, you take the message, which is a vector, multiply it by this thing. A key feature that we might be interested in is what is the weight of the resulting code word. How many zeros does it have? How many non-zeros does it have? And in sparsification, you can just think of some way of compressing some huge code which may have lots and lots and lots and lots of coordinates, and compressing it into a small number of coordinates, which roughly tells you what the weight would have been. Okay, so that's the task that we're going to solve. And the reason it was not looked at ever before is because, this is not a natural question to ask about error correcting codes. Okay, and you'll soon see why it's not really a great question to be asking about that. But the reason we were really motivated by this question is because, but the one instance that we've talked about so far, which is graph sparsification, is a special case of code sparsification. Okay, so why is it a special case? If you consider a code generated by the following, so if I have some graph G, which can also be viewed as the generator matrix of some code, look at the incidence matrix of this graph. And let me draw the incidence matrix. So I'll try to be consistent with this. Draw the incidence matrix like this. So these are the vertices, the columns, and the edges are the rows. And you put zeros except in the two endpoints of an edge on any particular row, and you consider this generator matrix. If you multiply this by any vector of zeros and ones, sorry, we went on the right. This corresponds to picking a subset of the vertices labeled 1, another subset of the vertices labeled 0. And if you do this multiplication mod 2, then what you get is the cut, the set of edges which are actually going from one side of the vertices to the other, from the 0 side to the 1 side. Okay. So this is, it's natural to ask the question, can I take this matrix and sparsify it? But now I can say, why consider only this matrix, only incidence matrices or graphs over here? Why not general matrices? Why not arbitrary fields and whatnot? And you can still ask the same question, what can you compress this? And that's the kind of question that we're going to be looking at today. So the answer turns out to be roughly that every code can be sparsified. What does it mean? How well can you hope to sparsify this thing? You cannot sparsify the identity matrix any way, right? I mean, if I take a subset of the rows of the identity matrix, that corresponds to some code, and you can't sparsify that. I have to tell you which rows are present and which ones are not present, and that's sort of the basic minimum information. So the most you can hope for is in an n by m matrix, I preserve roughly n rows and still capture the information, and that is something that we will be able to do. And as soon as we get this, we get sort of very easy consequences also to hypergraph sparsification. We'll show you the connection towards the end. And also, like, this suddenly starts opening up a whole field of answers and CSP sparsification that we didn't know about. So there were lots of nice motivations, but really one really good motivation was just to understand, what is this Karger's cut counting bound doing? What are we going to do with this over here?
I didn't understand the example of the identity.
Great, so sure. If I take take the identity matrix and take a subset of the rows over here, an arbitrary subset of the rows.
Okay.
No matter how you sparsify it, you have to tell me whether an edge is one of these rows is present or not. Okay.
Okay.
So there's definitely this n bits of information are more or less necessary to preserve this thing. So in some senses, if you ask me the question, how many rows of this matrix do I need to tell you about? I have to tell you about n rows, n bits of information on this. I could probably make it a more sort of a clean example, but yeah.
So sparsification of a general code matrix, you mean you're going to drop, so for instance, in that picture, you're going to drop some rows, is that, or you're also going to take a linear combination of stuff and
Good. I'll only be dropping some rows. In principle, I could have done anything that would have produced a small amount of information, but today, the way I'm going to even measure the information is just how many rows have you taken in this thing. So let's stick to this picture of take a few rows. But once I get taken a few rows, I will also give you some additional information, which is the real number weight associated with each one of the rows, positive real number weight, and it's the weighted Hamming weight that will be very close to the correct value. Some of these things will have to have high weight, and some of them will have to have low weight.
So the goal is the query is supposed to be there is some message.
That's
There's the message, and I want to know how many ones are there in the final list.
Yeah.
Okay, so why not just take the rows that form a basis of this matrix? What would go wrong?
Then I mean, because I don't know what the matrix is, right? So
I see.
I have no idea what the matrix is, except just like in the graph case, I know it's a graph, but I don't know which graph I've been given. So you could think of this as so you have no idea what the matrix is except the information that I'm giving you. And I'm still telling you basically what would happen if I multiplied that unknown matrix. This is the weights I'll be getting.
Why can't we just, you said the weights are different, but why can't we just multiply them beforehand in this matrix?
the input matrix, let's think of it as unweighted, though we will allow it to be weighted in the results, but it's simple. The output matrix might need to say, well, this particular, so I think we'll get an example which will probably clarify this. So why don't I wait till that time? Okay, great. So gives us a bunch of results in CSPs, which I might talk about later. Yeah.
Have your original matrix, you drop some rows, and you provide me also a row matrix at the left, which is the set of weights.
Yeah.
And then for any query, which is a column, if you multiply the new matrix with that column and multiply on the left by the weights, the final scalar that I get is the value that you would have got initially if your left matrix was all ones. Correct. The right matrix was different.
Correct, yeah. So, right, so the way Jackman is describing it, right? So you're going to have some, is this the way it would be?
Yeah.
Yeah. So I'm going to tell you, I'll give you a collection of weights, etc. And one constraint, the main constraint is that the number of weights which are non-zero here is got to be small. That's like picking a small subset of rows. And now we are saying that when you multiply it by this, then this, you get the same results roughly for every one of these matrices, vectors as you would if you multiplied it by just this matrix and that. Okay. So, and I can always, so somehow compress this part of the information. That's all that needs to be published about this matrix to tell you what these products are looking like. Okay. Great. Thanks.
Connected to the Karger algorithm, so there it almost looks like you're combining columns. So you pick a random agent perhaps.
Right. So that shows up in the analysis. That's not what you're doing for the sparsification is one process,
And
the group involves another thing, and we will get to that same. In fact, let's get to that right now, I think. So let me just briefly say a few theorems. So the main theorem that I'll focus on today is this one, which says every linear code can be compressed and compressed to roughly nearly linear size. The formal implications are written down. So in particular, if you have the code going from k elements over fq to n elements over fq, the total number of bits of compression will be like k squared log squared q. So it will be a much briefer matrix, a smaller matrix. On the other hand, if you just want to say, okay, how many rows did we preserve? It's roughly k times log q. And you can extend it to various abelian groups and other higher degree polynomials. I won't talk about this today. So, but you know, these things exist. And as a result, you get a bunch of results on CSPs where we can start saying lots more general things that were previously known. But let's not dwell on that. So let me just jump into the proofs because I think these are the fun things in this thing. And let's start with graph sparsification, the Karger and Benczur Karger results. Okay. So first, before we get to that, let me just sort of address one question that you might have at the back of your mind. Why don't we just pick a random subset of these rows in a graph with n squared edges or something? Why don't we just pick n edges at random and say that should be pretty good? And the thing is, this is probably a pretty good idea if you want to get an additive approximation. So if you want to count every cut to within plus or minus epsilon times the correct number, this will do perfectly well. And this is what your Chernoff bounds and so on tell you are going to work very nicely. But if you want a multiplicative approximation, this is not going to work. And in fact, I mean, if you look at a graph like this, is the biggest example of a dumbbell I could find online. So don't think of, this is not 5, this is a million, and that's a million. And there's one edge going across. Well, unless you actually sample this one edge for the cut that puts all of these vertices on one side and all of those on the other side, you will return the number 0, which is not a 1 plus minus epsilon approximation to the number 1. So somehow or the other, you do have to, as soon as the graph has a very tiny cut, you have to sample a lot of vertices, edges before you can actually get this thing, or you have to use non-uniform sampling. And we will have to do both. In fact, observe graphs that look like this. We'll say how to do this. So how does Karger's thing work? It's this cut counting bound, which is the crucial step, and that's where it gets to this question that Piyush was alluding to. It comes this claim that a graph which has a cut of size c, minimum cut of size c, how many cuts can it have of size alpha times c? Alpha is some constant in your, should be a constant in your head, 10, 20, etc. How many cuts can it have? The way Karger analyzes this is the beauty. I mean, I don't know, Jayakumar and I were around when these things came around. It was a sort of shocking result. By now, maybe many of you have seen it. How many people might have seen this Karger's cut counting? There's a few people in the audience, not. Okay, great. So you fix some particular cut which has at most alpha times c edges. I'm going to give you, so you fix the cuts S. I don't know the cut S that you have in your mind. I'm going to give you an algorithm which will produce this cut with some positive probability. Okay, the probability will be n to the minus 2 alpha. It implies that there can be at most n to the 2 alpha such cuts because I produce that cut with this probability without knowing anything, getting anything new. What is my algorithm? My algorithm is I will start contracting edges randomly. Pick a random edge in the graph, contract it, pick another random edge in the graph, contract it, and so on. Keep doing this till I'm left with 2 vertices. Okay. By contracting, I just mean merge the 2 endpoints. If there are self loops and all, throw them away. But if there are parallel edges, keep them in parallel. Okay. And repeat, always uniform. So one thing that's happening is throughout this process, the graph's cut size cannot be shrinking. So there are still at least 3 edges crossing the cut, crossing every cut. I think that's important. Yeah, that is important because it says when I'm left with I vertices, let's say I'm I steps from the end, I'm left with I vertices. How many edges are there in this graph? Well, the minimum cut value is C. Every vertex must hence have degree at least C. So the total number of edges must be at least I times C over 2. Okay. What's the probability that when your I steps from the end, that the edge that we choose to contract happens to be one of these alpha C edges from our cut S, from your cut S? Well, there are 2 alpha C edges that could be from the bad set. There are there are alpha C edges from the bad cut and IC over 2 edges overall. Probability is exactly that quantity, 2 alpha over I. Probability that an edge from your cut is not chosen is 1 minus 2 alpha over I. And you just take the product of this over I going from n down to 1. Okay, that's the probability with which your cut will be output. You take that product of those numbers, it just turns out to be something like n to the minus, it's at least n to the minus 2 alpha. Does this make sense? Questions about this? It's a very nice, simple process, and it proves that the number of things is great. Let me go from this cut counting one to the proof of both Karger and Benczur Karger, and that should be fun. So Karger basically said, okay, I'm not going to get you the linear number of edges, but let's just tell you that already graphs have non-trivial sparsifiers. Works very well in sort of expanding graphs where the minimum cut size is it's a moderately expanding graph. So where the minimum cut size is sort of uniform across the thing. If you pick I don't know exactly how to express this quantity, but m over, if this quantity m over c is roughly n, then this is a very good algorithm. If it is much worse, it's not going to be such a good, such a sparse cut. So he just says sample 10m over c log n edges. And now what's the probability that a particular set of size alpha c is not going to be sampled well, meaning you did not sample enough edges from this particular, an appropriate proportional number of edges from this cut? Well, the probability of that is going to be like something like n to the minus 10 alpha. Okay, because that's related to the number of things that we are sampling and the size of this cut. Okay, you're going to see some exponential decay in alpha C, but we are also sampling that many things. So you put it all together, you're getting a pretty good bound. And so the probability, but then the number of cuts that you have to take a union bound over of size exactly alpha C is at most n to the minus 2 alpha, n is at most n to the 2 alpha. So the probability that there exists a cut of size alpha times C is this n to the minus 8 alpha, still pretty small. And now that's small enough that you can do union bound over all alpha from 1 to n. So this gives a very simple application which gives a counting bound, but it's not the optimal answer. It doesn't tell you how to sample from graphs like the dumbbells, where if you just do uniform sampling, unless you're sampling about n squared edges, you will not sample the middle edge. So what should you do? Well, Benczur and Karger came up with a more sort of intricate analysis, and they defined something called a strength of an edge and so on and so forth. But in the course of our proofs, we actually came up with a fairly clean proof, I think, which hopefully fits in the rest of the page. And I'll tell you about that. So what's our proof? So here's what we're going to do. So really think of M as starting point of the whole space. Let's say M is n squared. Okay. You have a very dense graph, like the dumbbell, and has a very bad minimum cut. So let's say C equal to 1. Okay. M is n squared, C equal to 1. If you did Karger naively, you would be sampling n squared edges. That's kind of it. M over C is n squared edges, is what you would be sampling. Okay, so you wouldn't have been gaining anything. Let's show you how to improve on that over here. So what we are telling you to do here is to say, look at all cuts of size roughly square root of n. Okay. If there is any cut of size square root of n or less in the graph, remove those edges, throw them away. Okay, and throw them away and collect them in a graph called G0. So anything which has square root of n size cut, put them in the graphs G0. At the end, you'll get a bunch of connected graphs, each one of which has minimum cut value at least square root of n. Okay, so G1 to GT are the remaining graphs, each one has a minimum cut value of square root of n. G0 is the set of things that you remove, which had, because each edge was participating in the cut of size at most square root of n. Okay. How many edges did we have in G0? Well, each time I remove the square root of n edges, I've divided the number of graphs, number of connected components into one more. I can't do this more than n times. So the total number of edges in G0 is n to the 3/2. And G1 to GT are all graphs which have min cut value of at least square root of n. If you just blindly apply Karger to G0 and blindly apply Karger to all of these and put them together, you would have a minimum cut of size n to the 3/2, which is already better. Okay. And that's it. So this is all we're saying, just keep recursing the same way, keep going down for general M and C, and this is the formula that you should use. And each time you do this, you will be improving the ratio of M over C till it becomes nearly n, and at that stage, Karger is great. Okay. And that's it. This actually gives you an n polylog n sampler, which is non-uniform. The only thing that you have to be sure to be careful about is at the end, you take a sampler of G0 and you'll take some samplers of these. And you just want to make sure that you weight these more heavily, because each one of these, these graphs will be sampled very rarely, more sparsely, and this one will be sampled more densely. So you want to make sure that each one is appropriately weighted by the minimum cut of the associated graph, and as long as you do that, you're in great shape.
Why not genus sampled more rarely?
Because these have min cut values of square root of n, and Karger says that if you have min cut values which have square root of n, you should sample them at rate 1 over square root of n. And that's, and we are going to be roughly satisfying that condition throughout. It's just that being done more sort of naturally over here. There's no. So any questions about this?
I don't follow what you mean by recurse.
So recurse of G0 which means produce a sampler of G0. And recurs on G1 to GT, you can consider them as one single graph or multiple graph, however you want. For counting, it might be better to think of it as a simple single graph, which happens to have disconnected components. Disconnected components don't really bother us in the sparsifying. You'll never ever think there's an edge between the two sides. So produce a sparsifier of G0s, produce a sparsifier of this collection, and then bring them back together, which means you have some subset of edges and weights, some subset of edges and weights. But weight this side much more heavily now because you know that G0 is kind of sampled rarely, in this case sampled very heavily. Okay. Other questions?
So algorithmically, does it require actually going over all the cuts?
Does it require going over all the cuts? I think when you have to produce the first G0, you're looking for min cuts for sure and removing them. Yeah, so you do have to, okay, this is going to be an issue later on because here we needed to find min cuts and we know that we can find min cuts easily in graphs. There's going to be a problem later. Okay. All right, so this I think is already so if you haven't seen Karger before, this is great. I mean, I think it's a really beautiful idea, and each one of the steps, the previous analysis that somehow picking a random edge and contracting is a useful process, is very surprising, and then you use it to get bounds on the number of cuts of small size, and then to sparsify a graph. Each one of these was a beautiful idea, so it's great. So now we're going to try and do code sparsification in the same way. And again, because the codes are given by these tall, skinny matrices called the generator matrix, and we want to take a subset of the rows. So it would be very nice to have an analog of this cut counting bound, which says, oh, in every code of minimum distance d, the number of code words of weight at most alpha times d is at most k to the alpha, where k is the dimension of the code or something, or even n to the alpha, where is the length of the code. It would be very nice to have this, but it's not true patently because if you take any asymptotically good code, a code which has constant rate and constant relative distance, well, minimum distance d, the analog of minimum cut, is n or omega of k. You take codes of weight at most n, well, that's still order of minimum distance. There are exponentially many of those, whereas the cut counting bound will only allow polynomially many of those. This thing is also a very good reason why we never actually considered sparsifying codes. I mean, the reason that we ever wanted to build codes was because they should be asymptotically good, and asymptotically good codes don't need any sparsification. I mean, they're already pretty sparse. Okay, these are codes where the generator matrix would have k columns and n rows. Sorry for the swap of modifier, but that's the way it's written in the literature. And n is anyway order of k. So, you're not really interested in sparsifying natural codes, but linear algebra in the space is interesting, but also the notions of distance and so on turn out to be quite useful over here. So those codes don't really need to be sparsified, but if you do decide that you want to sparsify all codes, how would you modify this cut counting bound? And by the way, I mean, apparently people who've been working on hypergraphs sparsification already knew that the cut counting bound fails for hypergraphs, and they didn't know what to do about it, and they had to find lots of, it was a source of major complexity in extending cut sparsification to hypergraph sparsification. And today we'll see that actually there's no further complexity, almost, okay, modulo the right abstraction of the cut counting bound. So we need a modified cut counting bound. What are we going to get? This is the kind of a lemma that we want to prove. So informally, what we will say is that every code has basically inside it a very good subcode. Okay, so the subcode is going to look like more or less the following. So the code is given by this generator matrix. There is going to be a nice tiny matrix sitting in here, which generates, with roughly the same number of rows as columns. which is going to be very good code. You should not try to sparsify this part, leave it alone. And this part will be entirely zero. And this part I don't really care about much. Okay, or this part is more general, and this part is amenable to sparsification. Here, if I try to sparsify, that will be fine. What will be the idea? Why would this part looks like a graph where you have a good cut counting bound. This part looks like an asymptotically good code. And this part is, by the way, anything you want. This, let's say, it looks like a graphical. I don't mean that it's graphical in any combinatorial sense, except that the cut counting bound will work here. This part looks like a good code, asymptotically good code. This part is zero and that part is arbitrary. What will I do with this thing? I will, my random sparsifier will include all of these rows, which is fine because the number of rows is proportional to the number of columns. And sparsify this thing the way I would sparsify graphs. Hopefully this will work out. So that's roughly what the statement is. Formally, the statement is expressed in the following way. There's an additional parameter t. I'm given a code which is contained in fq to the n. So this can be over any field. One of two statements should hold. Either you have a code word counting bound. The number of, for every alpha, the number of code words of weight at most alpha times t is at most things that look like, polynomial and polynomial with exponent alpha. Okay. Or there is a code, a linear subcode contained in my code, whose support is very small compared to its dimension. So it's only t times larger than its dimension. Okay. So this parameter t is in my control. I can use apply it with any t, and then I get something that looks like it. So in some sense, I get to specify what the ratio of this number of rows to the number of columns is. And then you get it. Another way of looking at this particular theorem is that, and this is an easy corollary, is every row code will contain a once there is a code it contains a sort of subset of coordinates. This thing that I'm calling S. The size of the set S is at most the dimension of the subcode, dimension of the code times t. I think maybe this is okay. Yeah, maybe this is fine. So not too many coordinates. It's not, I'm not being too wasteful. It's proportional to the dimension of the code that I'm sparsifying. This is the number of rows that I can afford to throw away or sample. Such that once I remove those things, I have a cut counting bound. All right, so this is the code counting bound that we have. And once we have this code counting bound, the sparsification works pretty much exactly the same way as it did in Karger's and the Benczur Karger case. What we're going to do, in fact, with our simplified proof, it actually works kind of seamlessly because we didn't really, there are no graph theoretic notions like what's the strength of an edge and what's a vertex, etc., that's coming up over here. We'll just take this parameter t that was given in this previous thing, which up to us to choose. We'll choose it to be somewhere between the actual sparsification that we have of size n and the sparsification that we care of size k. So take the square root of t n over k and apply this corollary, and there will be one code which will be relatively small in size. It's not as small as we want, okay, but its size. So imagine you're looking at a code which has k columns and k squared rows. We will apply this thing with parameter t set to the square root of k. We will get something like k to the 3/2 by k size submatrix, which is what we call the good code. And the other side is amenable to the good sparsification. The good sparsification is not good enough to get a final bound. This code is not good enough to get a final bound. We cannot sample k to the 3/2, but we can recurse. And the next iteration, we will have k to the 5 ports over here and so on. So we can't keep recursing on this thing and we eventually get the bound. Okay. So all codes can be sparsified pretty much exactly the same way we were sparsifying graphs. Nothing really changed. We just did the same divide and conquer. Okay. Questions about this?
So why are you magnifying Sparsify C2 by square root?
Yeah, I don't know if I should choose, if I chose the number, right, and should it be square root of t is also not so clear. So, yeah, and I didn't say what the base case looks like either. So it's, I should be a bit careful over here. I don't know quite what the parameters is, but there is a possibility. At the end, we will see very low weights for coordinates sampled over here and relatively high weights for coordinates sampled over here. That's what we mean by that statement. I don't know whether the number should be exactly square root of e or t and so on. Okay, so I think square root of t is correct, but yeah, I'm not 100% sure. But there should be, at the end, once we produce a set of samples over here and produce a set of samples here, they will already have some weights, but you should be careful to make sure that the weights here remember the fact that there are k squared rows that they are supposed to represent, and these are only representing k to the 3/2. All right, so that basically says if you can do the code counting, then you're done. Now the question is, can you actually do the code counting? And the answer turns out to be yes, pretty much along the same way. We have another contraction algorithm in this case. And the contraction algorithm is maybe a little nice to view also again in this picture.
Can you flash the lemma unfortunately?
Sure. I can do it by walking twice. Okay, so maybe the lemma itself over there. Okay, and okay, unfortunately, I need to. Okay, this is what I think the thing does. Okay, so some of these rows of this matrix, bizarrely, you might not think of this as necessary in a good code, but some of these rows may be actually identically zero. Okay, so let's just not worry about those rows. Amongst the remaining rows, so let's say all of these are identically zero. Amongst the remaining rows, pick one row uniformly at random. And let's pick one coordinate where this is a 1. And we are going to basically do row column operations using this one row, which means that I'm going to make all the other elements 0 on this row. Okay, and repeat. So if it turns out that two of these rows happen to be identical and identical to this row that I chose, then now I've created a new code in which, so after I've done all this, I can basically throw away this column. I want to throw this column away. But now I've created a matrix in which two of the, some rows are 0 identically. So the zeros being identically 0, some rows being identically 0 is going to happen during the process. Okay. So that's what we're going to do in this matrix. We just pick a random non-zero row and pick one of the entries, which is 1, remove that one column and entry, and that's like what we call a contraction. We repeat and repeat and repeat. When do we stop? When the process has a dimension alpha or less. Okay, when the code is left, when the code that we are left with is this alpha dimensional space, we stop. And if at the stage we haven't run into obstacles so far, etc., and we are still left with the code, then we output a random code word. We say at this stage we ended up in case 1, which was that or I don't know if it was in case 1 or case 2. This is the case where you actually satisfy the thread counting bound, code counting bound. Okay, so we saw no obstacles to the code counting bound. We will satisfy it. On the other hand, what might happen at some point is that the support of our code might already turn out to be too small. Okay, so the support being the number of non-zero rows. If at some point the number of rows, non-zero rows is too small, smaller than t times the dimension of the code that we are looking at, then we stop immediately and output this subcode. Okay, and we say, oh, we are in the case where there was a small subcode which had relatively large rate. Does this make sense? The process makes sense. So it's clear that whenever this process stops and says, oh, case 2, it is the case that you actually found a small subcode which has a small set of coordinates where there is a large rate code supported there. That's why we stop. So what we want to say is, oh, if that's not the case, then we actually are proving a code counting bound. And how do we prove a code counting bound? We'll say, oh, let's fix a particular code word whose weight is at most alpha times t. And let's see what's the probability that that particular code word is output by this algorithm when we come to case 1. Assuming case 2 it never happens. Okay. So pick some word. Well, this is a code which has small weight. When you pick one of these rows and so on, so this code word is not non-zero in very many of these places. So you are going to, there are at most alpha t coordinate rows that you could have picked that might have done something to affect this particular code word, to remove this code word from your space. On the other hand, the support has size greater than t times the dimension. So the probability that you will somehow remove this code that you have in mind at this stage of this algorithm is at most alpha over dimension of c. Probability is not removed is 1 minus alpha over dimension of c. And now you take the product of this as the dimension of c goes from k down to t and k down to alpha. At the end, you're left with an alpha dimensional code. Well, there are at most q to the alpha code words. When I output one of those things, I'll probably output the one that you had in mind. So at the end, you end up doing this, and apparently the product of these quantities is in. It's more like it's not n to the minus alpha, it's 1 over n choose alpha. Questions about this? Yes.
Maybe not exactly about it, but so suppose we take a family of codes that we understand that 8,000 numbers. Those C1 and C2 have some semantic interpretation. See what is happening.
The C1 and C2 from the previous thing. So in any code that you looked at, they were all sitting in the top left corner. They are all codes of very high distance, but that's not so important. They were supported on a small number of coordinates.
It was constant, so they all
Yeah, exactly. So constant rate codes don't need further sparsification; they're already good. It's the big Hadamard code. The way we think of the a graph theoretic code is you start with this n by n choose 2 dimensional matrix. This is the mother code from which we're going to think. From this, I pick a graph into some subset of the edges, and now I want to tell you what is the subset of edges. So by sparsification, I pick out some smaller subset of edges, and in this case, the information that I need to tell you is not what is this bit vector over here and what is that bit vector. I just need to say which of these n choose 2 rows have been chosen.
So it feels like taking a code C and getting to C1 is like puncturing. It's in the sense that you end up you end up reducing the block length in the process. You don't care about what is happening.
No, okay, good question. So puncturing in a code typically refers to it's the same matrix. So puncturing would say, let's pick a subset of the rows. Maybe I'm going to probably pick more than many rows, but and I want some nice properties here. I don't care what happens here. But in our case, when we're looking at the C1, which is sitting here, we want to know that this part looks like a very good code. But the most crucial thing is we want this thing to look like a 0. Okay. This is what makes this not so standard as an operation. Okay, any other questions?
So I'm trying to just compare it against the Karger. So in the Karger, we sort of by Fiat that we will not contract a mean cut test. So it's alpha plus one because, and here that condition is being used. That condition is being imposed by this line. The analog of that will not contract a mean cut edge is this one. Is this?
If the code, if it's already a good code over the.
So there's, okay, I think the big contrast with Karger's is you would never run into this situation in Karger. You never needed to do this. So because a graph of min cut C on I vertices will have at least I times C over 2 edges, we know that the support size is always going to be large enough.
And there anyway not.
Yeah, in our case, the support size could get smaller, but if it gets smaller, we call it victory for a different reason and get out. Great, thanks. That was it. Okay, so other questions about this? So this is pretty much all the technical stuff in the talk. Maybe I'll just mention one implication and then we will stop. Okay. So this implication is to this hypergraph classification. This is something that people had actually looked at extensively. So Kogan and Krauthgamer gave a sort of, if I have an n uniform graph, R uniform graph on n vertices, they said, oh, you could sparsify it with roughly n times R edges. But R, I mean, what if R is a super constant? What if R is like n or square root of n or things like that? So what if our hyper edges are actually huge hyper edges? Then the sparsifications tend to be weak. Chen, Hanna and Nagla improved this bound to O tilde of n, but had to do a lot of extra work over there. And in our case, this hypergraph sparsification is one line corollary. Why? Because if I have an R uniform edge, I will just replace it by the vector. Now over here we have these incidence vectors which are 2 1s. Instead of that, I will replace it by a vector of having weight R, which will be 1s in almost all the places, and the final coordinate will be minus R minus 1. Okay, and this is over some large prime field, much larger than R in size. So if you take any cut over here, you will, which takes some of the ones and the other one takes the minus R minus 1 guy, there is no way this cut is going to have some edges, the vertices summing up to 0 mod Q. Okay, the only way to get the edges summing up to 0 mod Q is if you take all of these entries or none of these entries. So we counted a hypergraph cut. And that's it. So you just apply the code sparsification bound to this thing, and hypergraphs which did not have a cut counting bound like Karger's had a different cut counting bound, and you can still sparsify them and get the same results out of it. Okay. So there were many other applications of this nature in this paper, but I'll stop here. Maybe I'll start with the open questions. I should have done the open questions, because I think there's one or two maybe very interesting ones here. So this sort of came up in Piyush's question earlier. Karger's contraction is a algorithmic process. You find a min cut, you move something, you do something else, etc. So the entire sparsification became an algorithmic process. In our case, we need to know when does the graph, our code have a cut subcode which is large dimension and etc. This is a very hard question to answer. So in particular, can you find the support of some high weight subcode if it exists in our graph? We don't know how to find it. So since we don't know how to find it, we don't know how to sparsify our graph things. So this is an existential result, but these are not algorithmic results. Second thing that so getting algorithmic results will be very neat, and I think it's a nice class of questions. Another one is when it comes to the CSP classifications, it turns out by the time we're done with this kind of code sparsification methodology, we've got all the techniques wrapped into just this one thing. Every known CSP sparsifier is a special case of our sparsifier. And the only lower bounds we know is because, there is some constraint out here which looks like an AND of many variables, and this is something that's known to be not sparsifiable. And so the lower bound, this sort of technique is far away from the upper bound technique. We don't know how to make these match. So are there some new ideas? Can we do more sparsification? And I somehow feel CSP sparsification is a nice way to look at the broad class of questions overall. What is the structural property that allows us to sparsify? It'll be nice to understand those, and getting new ideas there will be nice. Thanks. I'll stop.
Is there a spectral analog of graph or?
Right. So we tried to. Is there a spectral analog? And we would have loved to see something like that. We couldn't find anything. There's no. We couldn't find a spectral analog of the notion of minimum distance of a chord either, which would be something that would be interesting to explore. Is there something? Because for many other reasons, it may be, I mean, just like, min cut is easy to find. Sparsus cut is hard to find, but spectral analogs tell us something interesting. So if we could find some spectral analog of minimum distance of a chord or distance in chords, that would have been an interesting concept, but we don't have it yet.
Madhu will be around for a few more days of this week. Particularly, he'll be certainly around tomorrow and on Thursday.
Okay, thanks.
Try to get you on.
Not